If you're a Delphi or C++ builder developer working with FireMonkey, you already know just how powerful it is for building these beautiful cross-platform apps. But there's this one fundamental pattern, this sort of secret weapon that really separates a good UI from a truly great one. Today, we're going to unlock that key to a perfectly smooth, flicker-free user experience. So let's start by digging into the very problem this pattern was designed to solve.
We've all been there, right? You're building an application, it's packed with data, and then you start to see it. That dreaded stutter, the flicker, the lag, it's that exact moment where a really slick user interface starts to feel, well, clunky and just unresponsive. And this isn't just a minor annoyance, it's a genuine performance killer.
So what is happening behind the scenes to cause all this? It's a phenomenon with a great name, layout thrashing. Imagine your app is trying to be really helpful. You change a control's width, and it immediately recalculates everything. Then you change its height, and it does it all over again. Now multiply that simple action by hundreds or even thousands of changes happening in a second. Your application gets trapped in this vicious cycle of constant, totally unnecessary redraws, and your UI just grinds to a halt.
And look, this isn't some theoretical issue. This quote, it's from a developer on Stack Overflow, and it just perfectly captures the real-world frustration. Controls that don't show up, content that's missing, forms that seem to hide themselves. These are the classic symptoms of an underlying UI update engine that is just completely overwhelmed. This is a real pain point, felt right across the community. But what if you could just tell FireMonkey to wait? To just hold off on all that recalculation until you're completely finished making all your changes? Well, you can. The framework provides a simple, really elegant solution that's baked right into the core of every single control, the begin update and end update pattern.
The whole concept is just brilliantly simple. You call begin update, and it's like putting a do not disturb sign up on your UI. You can then add items to a list, resize controls, change properties, as many things as you possibly need to. The screen isn't going to flicker, it's not going to redraw. Then, when you're all done, you call end update. That's the green light, the signal for the UI to perform one single efficient update, rendering only the final result.
And the structure you're looking at here is absolutely critical. This is not just a recommendation, this is the essential, bulletproof way to implement this pattern. By wrapping all your UI modifications inside a try finally block, you guarantee, and I mean guarantee, that end update is always called, even if an error pops up in the middle of your code. This is what prevents your UI from getting stuck in a non-updating state forever. What's so powerful about this is how the pattern is specifically tailored for different controls. So for a T-list view, for example, it completely stops that constant recalculation of item indexes and that really annoying scroll bar jitter you see when you add a bunch of items. For a T-grid, it intelligently syncs the data model with the visual columns all in one go. And for something like a T-memo, it prevents the massive overhead of reflowing all the text and fixing the caret position with every single tiny change. So we know that it works, but what's the actual magic happening inside the FireMonkey framework? Well, the mechanics are surprisingly clever, and it all kicks off with a classic computer science concept. The entire system is built on a very classic computer science concept, a semaphore. In this case, it's really just a simple counter. When you call begin update, the counter goes up by 1. When you call end update, it goes down by 1. And the UI is only allowed to redraw itself when that counter is all the way back at 0. Simple as that. All right, let's break down the key players inside the T-control class. First, you've got F-updating. That's our semaphore counter we just talked about, keeping track of how many begin update calls are currently active. Next, is-updating is just a simple Boolean property that lets your code quickly check, hey, is that counter greater than 0? But the real magic, the real star of the show, happens in do-end-update. This is the method that's only triggered when that counter finally gets back to 0. Its one and only job is to kick off the single, efficient, realigned call that renders the final state. And this counter is precisely why the whole system is so powerful. It handles nested updates flawlessly. You could have a high-level procedure called begin update, and then that procedure could call 5 other methods that each have their own begin update and end update blocks. The F-updating counter would go up to 6 and then slowly come back down. The UI won't redraw, not even once, until that final, outermost call brings the counter all the way back to 0. It's incredibly robust. Okay, so this pattern has been around for a while. You might be asking, why are we talking about it right now? Well, because with the latest advancements in RAD Studio 12.3, this pattern has gone from being just a best practice to an absolute game changer for performance. See, FireMonkey isn't relying on older graphics APIs anymore.
With brand new support for Metal on Apple platforms and Vulcan on Android, it's plugging directly into the metal of modern GPUs. This is a massive, foundational shift that unlocks some incredible performance potential.
Let's just look at the concrete differences this makes, especially on Android with the Skia rendering engine. Under the old OpenGL ES model, you had a high CPU load because of all this driver overhead. With Vulcan, that's much lower because the framework gets explicit control. Then there's multi-threading. OpenGL was pretty limited, mostly serial. Vulcan, on the other hand, was designed for multi-threading from the ground up. And finally, all of this translates to energy efficiency. The old way meant a higher drain on the battery, while the new way is optimized for mobile power saving. The bottom line for your users? Faster apps and longer battery life. It's a huge win.
So here's the crucial point, how this all connects back to our update pattern. Because Vulcan is multi-threaded, FireMonkey can now use that do not disturb time, that period inside a begin update and update block, to prepare all the rendering commands on background threads. So when you finally call end update, most of the hard work is already done. The result is an almost instantaneous redraw with virtually zero stutter.
And believe it or not, it gets even deeper. With Android 15 moving to 16 kilobyte memory page sizes, that's up from 4, the actual hardware-level cost of inefficient memory access has gone up. Every single unnecessary memory operation caused by that layout thrashing is now more expensive. Using this pattern isn't just a software trick anymore, it's about respecting the underlying hardware itself.
So we've covered the problem, the solution, and why it's more critical now than ever before. Let's wrap all this up with a clear, actionable checklist that you can take back to your own projects right away.
Here it is. Number 1, treat every major UI change like a transaction. That means wrapping any block of modifications in that try finally block with begin update and end update. Second, if you're targeting Android, you've got to enable Skia to get all that Vulcan goodness. Third, don't block your UI thread with database or network calls. Push that work onto a separate thread. And finally, do yourself a favor. Go through your code base. Search for a begin update and make absolutely sure every single one has a matching end update.
And that really brings us to the final question. After seeing how this one simple pattern connects to everything, from your code structure to modern GPU pipelines, and even down to the hardware memory pages, is your UI truly as fast, as smooth, and as efficient as it possibly could be? The tools are all there, and now you know the secret.